Play some spooky music here.
Let's move into the details of how this thing is implemented. Now we have to talk a little bit about the series of music and sound. So because we are actually imitating a piano, we know that in piano there is 88 keys, and that is categorized into 7.5 octaves. And in each octave there is 12 keys, 5 black, 7 white. That's from C to B. For simplicity, we are not gonna implement the half, so we're only gonna implement 7 octave, that is from C1 to B7. In piano, we know that because the piano is actually tuned at A4, which is always gonna be 440 hertz as its frequency. And so what we do is we record down in our application the 12 basic frequencies, as we call it, that is from B4 to C4. So we are gonna record these actual frequencies into the application, and we're gonna deduce the frequencies of other keys from these 12 basic keys. So as we know, if we increase an octave, for example, from B4 to B5, we're just gonna double its frequency. So if it's A4 to A5, we know A5 is 2 times 4040, that is 880 hertz. So we are going to do the same thing to all the other keys. If it's A3, we are just going to half its frequency. So A4 is 440, A2 will be 220. And we will apply this thing to all the other keys. And this is the formula we're going to use. So we know the frequency of a key is the frequency of its basic key in B4 multiplied to the power of n minus 4. N is the octave it is in. So if n equals to, let's say 6, so we know the basic frequency of 6B will B6, that is, will be FB4 times 2 the power of 2. So yeah, this is the formula we're going to use. So since we want to imitating the sound of piano, word for how a sound will sound like, the word is actually the timbre of the sound, which means if the sound will actually sound like a piano or a whistle or anything. And the timbre is determined by overtones. As we know that in nature, no sound will actually be a simple sine wave. Actually, it will consist of multiple small components, and these components are called overtones. Overtones can be classified into harmonics and non-harmonics. Harmonics are just those components that have the frequencies of which are integer times of the basic frequency. So if it's integer, it's harmonic. If it's non-integer, it's non-harmonic. And we know that to determine a timbre, harmonic components are actually the most important. So here we can see a few graphs that telling us what components are actually in some kind of sounds. The first is this is the factory whistle, this is the soprano, and this is the piano. So we were gonna refer to this graph, and we are adding overtones to our synchronizer.
So how do we implement the system based on these three parameters, which is the acceleration x, acceleration y, and acceleration z, to implement the 12 keys we just mentioned? First, we divide the whole system into 3 levels. At the first level is acceleration x. because the acceleration x has a range of minus 0.4 and 0 to 0.4, due to based on our experience, it has such range. So if the x is above 0, we will add 1 to a number called to the weight. Okay, so at first weight is 0, right? If the acceleration x is above 0, bigger than 0, then the weight will add 1. If it's smaller than 0, it will add 0. Similarly, for acceleration y, if the acceleration y has a range of from minus 0.6 to 0.6. So if the y is smaller than minus 0.2, we will add 10. Similarly, if it's between minus 0.2 to 0.2, we will add 20. If it's above 0.2, we'll add 30. And for acceleration z, it's a little bit different because we find the range of z is from 0 to 1.5. So it's if z is less than 0.75, we'll add 100. If it's above 0.75, we will add 200. Why we implement this weight is because we want to decide which key to play based on these 3 parameters. We want to map one weightage to one frequencies for the basic frequencies here. So as you can see here now, at the lowest level, after all this weightage sum up, we can actually get 12 different weightages, right? From 10 to 231. And each weightage will match one frequency for the key there in the piano. So this is how we decide which frequencies to play based on the 3 parameters we have.
So now let's see the user interface of this application and how the user might actually play with this sound synchronizer. So as you can see in the center, this is the waveform graph, which is going to show what waveforms is actually going to be played. Now let's start this thing, and we can see as you move the thing, the waveform is actually changing, and this is actually showing the waveform that is currently played. Now, actually in this synchronizer, we have 2 other features. The first is you can actually change the octave. So we know in piano that there is 88 keys, and they are categorized into 7.5 octaves. But here we only implemented 7 just for convenience. So you can choose from the lowest, which is 1. You can see the waveform is actually changed, to the highest, which is 7. Yeah, so you can change from it. The other feature is octave, because now the music is actually formed by a single sine wave. The sound is not going to be very natural. So to make the sound more natural, we are adding overtones to the waveforms. So this button is for turning on the overtune. So if you turn on, you can see now it's not a single sine wave. It's got other harmonic components adding to it, and the sound will sound more natural. So also this here is showing the basic frequency it's now playing at. So
okay, now here we are going to look at the block diagram of our program here. As you can see, is this loop. First of all is the structure. The overall structure of this program is a iterative structure, which will continue running until we click the stop button here. And within the loop, within each loop, we get all 3 acceleration parameters from the global variables. As you can see here, the 3 boxes will give us 3 global variables, which is acceleration x, acceleration y, and acceleration z. And we mentioned previously that our logic to divide all these to decide which frequency to play based on these three parameters is implemented here. The x value will, if it's above 0, we'll add 1 to the weightage, and if the y is above 0 point, we'll add 20. If z is above 0.75, it will add 200, right? So this is how the weightage is added, and at this point, the three weightage are added together, and we will enter a case structure in this black box. The case structure has 12 cases, which is exactly the 12 cases we implemented in the logic we described. And these 12 frequencies, 12 weightage will each of them will match with one frequency. As you can see here, if its weightage is 210, the weightage is 4661.164. And if the weightage is 120, it's 440. And weightage is 230, it will be 369.994. Okay, so at this point, the program will already decide which frequency to play, right? And here is actually this part is for the octave selection, and this is the bar control you see in the front panel interface. And at this point we will do some implementation about the basic frequency to get the actual frequency based on the octave you select. And after this point, it will be the frequency in the octave you select. And this part, the one I'm circling here, is actually for the overtune. As you can see here, because previously we from the website we know that for pianos there will be majorly there will be two harmonic noise and harmonic overtones. One of them is actually the twice the frequency of the original signal, and one of them is 3 times the frequency of the original signal. And for the twice size, there will be actually the amplitude will be 3/4 of the original signal. In this case, the original signal is at 20 ampere, 20 amplitudes, and for the first harmonic will be, so we will choose 15 amplitudes, and for the third harmonic we will choose 2 amplitudes, which is 1/10 of the original signal. Okay, so and these three blue box are actually the waveform generator, the sine waveform generator in the lab view. So we will provide the frequency from this LAN, and we'll provide the amplitude. They will construct a sine waveform. And we add all these 3 sine waveforms, we'll get the final waveforms to play. And we have a switch here, so if you decide you don't like the overtune, so you can turn it off, and the system will only play the original signal, which is a perfect sine wave. But if you decide to turn it on, you can play the signal with the sound with some overtones, which is relatively more natural. Okay, so after here, you can see we got the final waveforms to play, and in this box is the play waveform module, play waveform toolbox in the lab view. So with this tool, we can actually play the data setting here, and the waveform graph here is just to simply show the graph of the waveform, so you can have a better understanding of all the components we are playing right now. So this is pretty much about the logic diagram, the block diagram of our lab view program. Hope you like it.